So thank you all for coming. Going to talk about the largest design build project to date in the state of Rhode Island. It's called the 610 Connector Project. The project involves design and construction of 5 new elevated bridge structures to replace and reconfigure the existing interchange. Due to a lot of site logistics and headroom restrictions, and also the depth of bedrock at the site, initially 50-ton micropiles were proposed for the project. We have a very typical sand and silt. Oh, there we go. Perfect. Now we're in business here. So, again, biggest design build project in the state of Rhode Island. We're going to talk about the foundations and sort of the post-bid, post-award design phase testing program that was done to essentially optimize and really improve both the support that the foundations could offer, and also just some of the construction benefits that existed. So, quick outline of the presentation. Want to talk a little bit about safety, just because when we're driving piles, I think that's a pretty major concern. And frankly, a lot of the folks in our industry who are on site may not be on pile driving sites on a daily basis. So, just want to provide a little bit of a brief sort of bullet points of what we as engineers can be doing and should be looking for as far as trying to maintain safety, when we're on pile driving sites. It's a real picture of a precast pile going through a vehicle, and thankfully no one was injured, but I mean, that's certainly the worst case scenario, and hopefully that resonates with folks. 610 Interchange location, backside of Providence, west end of Providence, just west of downtown. It's a sort of a cutover highway that connects, that sort of loops around I-95 in downtown Providence. For those familiar with it, it's a bit of a mess, and when it was designed in the 50s, it certainly was never intended to carry the traffic loading that it has today. It links 3 major commuter roadways. It's the essential artery for anyone living in the western suburbs. Currently it exceeds 100,000 vehicles daily, and when we were out there working, it was pretty much consistent that there was always vehicle traffic stopped at this interchange in all directions, at all ramps. It's just not designed to modern traffic standards. In addition to that, RIDOT had deemed all these bridges structurally deficient, and while having performed segmental repairs in the past, it really didn't. It really only put a Band-Aid on the structure, and it really wasn't holding up. Quick overview of the site. You see, you've got northbound, southbound traffic on the left-hand side, as well as the interchange to 6 and 10. The one piece that's missing here is that you cannot actually get from Route 10 northbound to Route 6 westbound. There is no connection there. You have to get off and go through a neighborhood to get back onto Route 6 westbound. So one of the big advantages or benefits to this would be to actually connect the Route 10 northbound to Route 6 westbound through a large flyover structure. Current conditions, as you can see, this bracing and support system has been in place since the 70s, and is actually corroded to itself. It's beyond its useful life, and this is really what's stitching a lot of the structure together. So just a quick picture there. Again, just some other existing conditions for what we have here. So project itself, again, $410 million. Some of the basics here: RIDOT. We started our work in early 2018 and basically continued the test pile program through the fall of 2018. If you're familiar with Providence, New England subsurface conditions, you've got a pretty typical Providence profile here with some fill and organics on top of what we call the Providence silt, which as described here, medium dense silty sand varying silt content gives it sort of the sensitivity that we're used to. And as we'll find out, this silt is extremely sensitive to dynamic installation and pile sort of skin friction conditions. So originally the job was designed as 50-ton micropiles installed into the medium dense Providence silts, about 100 feet long, 110 feet long were the initial designs. And a big part of that was because of the low headroom associated with the existing structures, the fact that the existing structure had to be replaced in the same footprint as the new structure had to be replaced in the same footprint as the existing. So it was an obvious drilling job. However, it wasn't necessarily the best foundation solution given the stringent loading conditions, both axially and in uplift and even in lateral. With the high overpasses that they were building in the flyover pier, those loads were really pushing the envelope of what a 50-ton micropile can do, and so you were left with an initial design that sort of was looking at 40 to 60 micropiles per pier, with a total of about 18 to 20 piers in total. And so you look at it, our best guess was 44,000 linear feet of micropiles. So GTR possessed prior experience in Providence from another RIDOT interchange project where different piling solutions had been introduced, one being these 16-inch diameter taper tube piles. And so we approached the design build team post-bid and said, look, we understand you've got a drilled foundation here. However, we have data and we have experience to suggest that in these similar soil conditions, that a 16-inch taper tube could potentially perform much better than these drilled foundations. And so we really, went out on a limb and prepared essentially a proposal, basically, to say, hey, look, we've got prior experience. Let's see if this experience plays out successfully and gives us, the information that we're looking for, and maybe helps us, basically value engineer the foundations on this job. Just looking at some brief overview of sort of the pros and cons on this site. Reasonable capacities for the micropiles, 50 tons, very achievable in these soil conditions. Again, some of the the basic advantages of micropiles: low headroom, noise and vibration concerns will be less, and smaller equipment. But the big con here is the frictional capacity. Once you achieve about 100 feet in the ground, you cannot attain any additional load in these micropiles. It was pretty clear that making them longer wasn't going to make them have higher capacity, and so it became clear that you had a very limited frictional capacity, and frankly no end bearing capacity. It's not like you're drilling these into rock is 200 feet deep. It's not really an option. So we approached with this driven pile foundation, again, higher capacities, especially when you add a closed end, and obviously the advantages of driven piles: shorter installation times, no spoils. But again, the same con exists with these pipe piles, even with closed-ended, that you don't demonstrate increased capacity with depth. Our data will prove that as we move forward with the slides, but the key con here in this soil conditions, and we have significant experience in Rhode Island, is that after a depth of 60 to 80 feet, you're just driving deeper without showing any additional capacity, whether it's in skin friction or in end bearing. And again, the rock 200 feet deep didn't really create a scenario where driving to bedrock was efficient or appropriate. So we had prior experience with taper tubes, and our experience told us that we could achieve higher capacities for shorter driven lengths compared to the pipe piles, and certainly compared to the micropiles. We understand too that these pile types can develop higher shaft resistance in these types of soils compared to other situations where you're in more cohesive material or driving to bedrock. High durability of the pile was also a consideration. There is fill and rubble, and while we did pre-excavate or pre-drill, you get all the advantage of a driven pile, and I think, additional advantages given the soil conditions. And I think that's a key to this whole job, is that the soil conditions were so sensitive that this pile type became, essentially a really effective solution. So we wrote a whole construction feasibility and drivability summary plan. We basically wrote a proposal to say, hey, look, if you work with us and we can go out there and perform this testing, we think we can develop a better solution. And so this was our proposal. Drive piles at 2 test sites, drive both pipe piles and taper tube piles to evaluate, directly the performance of both. Try to mitigate some of the concerns for neighborhood noise by, and vibration by doing some of these environmental studies, and then obviously doing dynamic and static testing. So we picked 2 sites that kind of demonstrated the overall soil conditions across the site. We have a site that was located east of the existing Amtrak right-of-way that sort of cut the job in half, and then we had a site on the west end where the soils were less, were more, I guess, were poor. They more organics, deeper sandy, silty layers, thicker sand silt layers, less dense overall. And this was sort of the worst case scenario area, this B11 boring. And so that's why we obviously chose it, because we want to kind of pick our worst case scenario for determining, where to test. So the first step was to install these piles, pretty typical dynamic test pile program, EOD testing, and then coming back, 5 days later and evaluating time-dependent capacity, because that was the real key here. We were seeing blow counts of 15 to 25 blows a foot during initial drive, and capacities that were well less than what we were shooting for. And I guess that brings me to something I didn't want to gloss over. Our initial, research study and our initial sort of Class A prediction was that we expected, or we assumed, these piles could achieve approximately a 400 kip ultimate load. That was really our goal. In meeting with the project team and trying to discuss the feasibility of this, we said, look, we can give you a 200-ton design load foundation, or 225-ton design load foundation, in lieu of the 50-ton design load foundation that you're considering now. And so, that was a big increase, right? That was what we thought we could do based on static analysis and weep analysis. And so, initially they were like, go ahead, go to this worst case scenario and show us what you can do. And so we initially put these piles in with dynamic testing, and we were pretty surprised, how little capacity we were seeing during initial drive. I mean, maybe 100 kips, maybe 200 kips, so really only about 50% of what we expected to see. And so really that time-dependent capacity in those Providence silts, in that silty sand layer, really became the key to this, and whether or not we could actually achieve significant enough setup to justify even static load testing. Because another piece of this puzzle and another piece of this job, and to try to make it more suspenseful, is that we really were only given sort of these task orders. Go out and do the PDA testing and tell us the results. If we like the PDA results, maybe we'll consider doing a load test. If we don't, we're just going to scrap the whole thing and go back to our micropile design. So for us, this was really, it wasn't a given at any point that A, that the load test program was going to continue, and B, that it was even going to be accepted when we were done. So this was a very critical piece of the first step of showing that these piles and this pile type could do what we had analyzed it or assumed or predicted that it could do. So we have, I think we're missing. Let me go back. This slide. Okay. So what we have here is a summary of the actual PDA data that was collected. And, we started with the west of Amtrak site, and we we're seeing, relatively appropriate capacities, I think, enough that with both the pipe piles, which were the labeled PP, and the taper tubes, where I think they felt comfortable with allowing us to continue. And so we ended up doing test piles at both locations, the east of Amtrak and west of Amtrak, and we were getting, capacities in the 300 to 300 kips with the pipe pile, 400 kips with the taper tube, and on restrike we were seeing some setup, but not unfortunately as much as we had hoped. We were hoping to get larger increases. In some cases, at the east of Amtrak, we did see a pretty large increase between beginning of restrike and end of drive. But on average, it was maybe 15 to 20%, and we were hoping to see larger increases with that, if only to kind of help really make this a slam dunk for us and our client to kind of pursue with. But we were able to show enough progress and show enough potential that they allowed us to kind of move forward with the static load testing program. So we really were interested in load transfer, understanding where the load was being resisted within the soil stratum and sort of those mechanics. And so we instrumented all of our test piles, all 4 test piles, with various strain gauge and inclinometer casing for lateral testing. And so basically we ran compression tests on all 4 sites, and we ran tension tests on 3 of those 4 piles, and we ran the lateral test. And we really wanted to see kind of how the how these 2 pile types, the taper tube and the pipe pile, would behave, and kind of evaluate if we thought we could use the taper tube. Now the pipe pile was always sort of the plan B, but the goal was to always prove that the taper tube was the appropriate solution here. So we have a typical load test plot, compression test, load test plot. This was our pipe pile, about 220 tons in ultimate capacity, 210 maybe, depending where you draw the line. And then you have our taper tube, which pretty clearly follows the theoretical compression line right up until we see a pretty pretty clear and instantaneous failure. And that's 280 tons, which is 25-30% more than what we had anticipated seeing with our models and with our pre-engineering. And we were pretty impressed. It was a pretty big exciting day, I guess, when I was out there running that test, and we were like, wow, we're just about at 280. It was I don't think I expected us to get that high, and certainly didn't expect to see this plot of load versus displacement. It was a pretty good day. So next, we're going to look at the actual load transfer information that we obtained during these compression load tests, looking at how the load was distributed within the pile. I think that the key takeaway here is the load transfer within the taper. The taper was 25 feet long, so above that it was all just standard 16-inch pipe, both on both pile types. But what you can see here is that the taper tube is really shedding all the load along that tapered section, and you're basically having you have a larger load being transfer along the tapered section, and B, you're not showing you're not relying on really any end bearing, which is important in these soils that were very medium dense at best. You're not getting a lot of dense soil at the toe of the pile to really provide that end bearing. And you can see here that with the pipe pile that you really are still relying on a lot of end bearing. And I think this is a pretty clear indication of how the taper tube works in terms of load transfer, and also demonstrates really the benefit in these soil conditions of the taper tube itself. Tension tests had similar results. This is from our pipe pile, and then this is from our taper tube pile. Now we understand certainly that the majority of the pile is similar, that they're both 16-inch pipe, but we feel like the taper contributed significantly to the higher tension capacity of these piles. Again, you can see the load transfer here And basically what it shows is for the pipe pile, a lot of the load transfer is being taken along the shaft, essentially above where the area of the taper is. Meanwhile, with the tapered piece, you can see more of the load being, resisted in that tapered section, which again, with really the large uplift loads that they were looking for, provided, I think, a lot of good information about how these would perform in practice. Looking at the lateral load test data, because taper is so far down, and a lot of these piles were driven 100 feet. The one area they're at 60 feet, the other area about 120. Not seeing a lot of difference between them, but they both demonstrated that in lateral, lateral capacity was sufficient for the design parameters. This is a quick summary of what we saw, and I think again the key takeaway here is that the pipe piles, the nominal compressive capacity was 280, 350 kips, and the taper tubes far exceeded that in compression capacity. And these are the static load test results. So it's all things being equal, the only thing we've changed is that 125-foot tapered piece at the bottom. In these soil conditions, it was quite obvious that the taper tubes well outperformed the pipe piles. Other advantages that we observed during the load test program, higher capacities at similar blow counts for the taper tubes. And, overall, we were looking at essentially 4 times higher ultimate compressive capacities than would have been assumed or would have been used for the micropile loads. And really the key to the it's money piece of this is that we were able to use this data and by collecting it, directly incorporate it into the final design. The designers on this job used the ultimate capacities, the site-specific ultimate capacities, directly in their calculation of the ultimate resistances that the piles could retain, could resist, and really use that to optimize the design. Other things we were able to disprove were that piling would create large vibrations and noise. That wasn't the case. We were able to show data that helped RIDOT convince Federal Highway and convince the city that pile driving wasn't going to be any more of a nuisance than any other construction activity. And we didn't see any observable settlement. Pretty successful pile load test program. And so what we're looking at here is a summary of all the new piers that were constructed. You can see there's 17 different substructures that ended up being founded on these taper tube piles. There were between 18 and 25 piles per substructure, depending on the size. And the original design, again, was something like 45 to 60 micropiles per pier. And so the key here is that with the increased testing, with the commitment by the design team and the design builder to really do this testing up front, we were able to take a job where they were assuming about a month worth of construction per pier, and they were driving out piers in 2.5 to 3 days. And so it became an obvious and clear savings both in time and money for the client. Just some photos now of some of the construction phase installation. You can see here a row of battered taper tube piles installed, in the existing footprint. And really one of the key advantages to this whole job was because the schedule for installing taper tubes was so aggressive compared to the drilled piles, the drilled micropiles, that they were actually able to demo the majority of the existing superstructures so that we could work without headroom restrictions. So what you see here is a section of the job where they were actually able to demo the overpass and allow us to work with no headroom restrictions. One of the things we did here, we did see is that we found there was a lot of existing utilities that were in this right of way for the highway, and we really had to work around a lot of that. So some existing foundations that were observed as well. So in summary, I think the real key and why this sort of fits into the It's Money theme is that we were able to demonstrate a 400% increase in axial capacity compared to the original pre-bid design. In doing that, we were able to, drastically reduce the construction schedule from 40 to 50 days per pier to 2 to 4 days. In addition, the cost of installing that foundation was 7 figures reduced compared to the drilled shafts, because the time was so much less. And in addition, it really advanced their construction schedule, because they were able to perform demo, which they assumed they would have to wait until after foundation construction to do. They were able to perform that in advance. So they're actually able to do some of the really heavy, deck removals and getting rid of girders and all that in advance before they ever drove piles, and still were, almost 12 to 18 months ahead of schedule after that. And again, my sort of commentary on this is, it's pretty clear that a project delivery method like design build allowed for this opportunity for innovation in a way that maybe a bid build job doesn't. It also clearly shows that the collaboration between the owner, RIDOT, engineer, was AECOM, contractors, design build contractors and suppliers. The taper tube folks were really important to this to help sell the idea. In the fact that the design build team was open to that because they had flexibility in their design approach. I would also say that it should be restated that on all of these jobs, whether you're testing to failure or not, that you should test in non-production locations with robust frames, so you can really establish site-specific design parameters, and not just proof test to 2 times what you want for a design load and assume it's good. You can really achieve more than maybe you think you can. And then the key is to use all that capacity. Don't just use what you need to get your design assumptions and move on. Really incorporate that site-specific data into the final design, because there will be a clear cost implication to your owner, to the contractor, to whoever, that shouldn't be discounted. And frankly, I think this shows that this piling solution, taper tubes, is feasible in New England. And this job is the first high-profile, high-value, large-scale use of taper tubes in New England in a sandy, silty subsurface condition. And I think that should also be remembered as individuals and DOTs and folks plan new work, because it's a new innovative solution. With that, thank you, Gerald. Thank you, audience. I appreciate your time.
Thanks, Seth, for a very interesting presentation. And it's nice to see a different type of pile being covered in this series. This is the first presentation that we have on taper tube piles.